Okay, so it's roughly going to be split into two parts, this talk. The first part is going to be a lot of basic results and how one might compute this new notion that I'm going to tell you called non-commutative rank. And the second part, I'm going to talk about applications to maybe tensor rank and quivers and Brass cantilever inequalities a bit. And if you have time, I might give some silly results that look strange. Okay, so I'm going to start with so let's F is always going to be an infinite ground field for me. Okay, an infinite field, and unless you have reason to care, it's the complex numbers. Okay, is that big enough? Okay, so I'm going to start with a little bit of a thought experiment. So I give you a matrix that looks like this. And I ask you, what is the rank of this matrix? Okay, it's not a trick question. Who knows what the rank of such a matrix is? Depends on? Let's just say A and B are elements of the field. Two. Why do you say it's 2? You've seen this matrix before. That's great. Okay, but what is the argument? So the argument is, if you notice clearly, this is a skew-symmetric matrix, and every skew-symmetric matrix has even rank. Yeah? It's a factor from kind of basically that. But I'll give you a simpler example, simpler reason. So L is negative of L transpose. Yeah? Now I take determinant is -1 to the 3. Yeah? Therefore the determinant is 0. Okay? But now I want to do it in a funny way. I want to do it in a funny way to set up what I might do. So one way to compute rank is Gaussian elimination, right? You do row and column transformations until you get a bunch of identities and a bunch of ones in the column. So the first thing that I want to do is I want to take the third row and I want to add b times the first row so as to get rid of this guy. Okay, so R3 plus BR1. This will give me 0, 1A, -1, 0B, -A, 0, and B times A. Yeah? Now, I will also get rid of this guy. And to do that, I will take this row, multiply it with an A, and subtract it. Okay, so R3 minus AR2. And what I will get is something that looks like 0, 1, -1, A, B, 0, -A, 0. And I will get BA minus AB.
That's 0.
Yeah, that's 0. That's right. Okay. And once I have a column with just a 1, I can get rid of the A. And once I have a column with a -1, I can get rid of the B. So I can do some column transformations, and I can get just this guy. And I will write this as the commutator of B and A. Okay? So this is evidence that the reason this matrix is rank 2 and not rank 3 is because B and A are commuting in the world that we live in. Okay? So if you were living in a world where B and A do not commute, you should expect the rank to be 3. Yeah? Okay, so now time for some definitions. So L of T1 to Tn is a matrix that looks like this, which is what we call a linear matrix. So in this T1 to Tm are indeterminates. They're just formal variables. and the x1 to, the xi's are n by n matrices, let's say, with entries in the field. Is that clear? So every element of this matrix is going to be a linear form in the variables t1 to tm with possibly a constant term.
Affine form in the way you define it.
Yeah, affine form with possibly, yeah. Linear form with a constant term has a better name. It's called affine form. So every entry is an affine form in t1 to tm. So let me give you an example. And I'm going to give you that same example. So L of t1, t2 is 0, 1, t1, t2, 0, minus 1, minus t1, minus t2. Yeah, that's okay. If I wanted to write it out in this form, I'd write it out as 1 minus 1 plus t1 times 1 minus 1 plus t2 times 1 minus 1. Is that clear? I didn't bother to write all the zeros, but okay. So now I'm going to define the non-commutative rank using this example, and it should be clear how you define it in general. So here are the two definitions. So the first one is the commutative rank of L, and it's what you might expect it to be. And okay, so you want to live in a commutative world and you want the rank, so you want to know what field these entries belong to. And what is the most natural field that these entries belong to? It's the function field, right? So you look at this, they're all linear functions in these t1 to tm, right? So you look at the function field, and in this case it's just t1 and t2. You consider it as a matrix with entries in this function field, and you take its rank. Yeah, and in this case, what is the rank? It's just got to be 2. And the second definition is that of non-commutative rank. And here's where, okay, you don't take a commutative field, but you want to take something non-commutative. And so let's think a bit about what does this field mean. So when I say function field in two variables, I'm literally saying start with the field f, put in two indeterminates with no relations except for commutativity, and see the free field that you can get. Yeah. Now I want you to do the same thing, but don't even impose commutativity. And what you will get will be a non-commutative field, which we have words for it. It's a division algebra, skew field, whatever you want to call it. Okay, and that has a funny notation, and I don't know who to blame for this, but we have no choice. Okay, and in this case, what is the non-commutative rank going to be?
3.
It's going to be 3. Okay, and what's the reason? The reason is, well, let's suppose you had t1 and t2 here, and you did the same sort of Gaussian elimination, but now living in this skew field, you would come all the way till here. Until here, it actually required absolutely nothing. Come here, and then you look, and you will have the commutator of t2 and t1, and you will realize, oh well, in the non-commutative field, whatever it means, that should be something non-zero.
And this rank now is non-commutative rank over a non-commutative field, which
Yes.
you haven't defined.
Yes, I will.
Over a non-commutative field. Oh, the full field. F is commutative.
F is commutative. That's right. F is commutative. But now this bigger thing is a non-commutative field. It's a skew field. Okay, so this is called the free skew field. Okay, so the natural question was, how do you define rank over these non-commutative fields? Okay, so how do you define rank over a commutative field? There are so many ways, right? You can define row rank, column rank. You can ask for the size of the largest minor. What else can you do? Image, dimension, whatever. There are a bunch of ways. So, but the right notion of rank in the non-commutative setting should be to go back all the way to row rank and column rank. The most naivest way of asking how many linearly independent columns there are and how many linearly independent rows there are. There's a little bit of a caveat. And So when you take linear independence, or you check this, you want to take your rows and you want to multiply them with some coefficients and add them up. Now if you're in the non-commutative setting, you have to question yourself, can I multiply on the left or the right, or do I allow myself a combination of both? Okay, and so let me just put this out. So in rank over any division algebra, any skew field, we will take this to be what I call the left row rank, which is equal to the right column rank. Okay, so left row rank means you can check for linear dependencies, but only by multiplying things on the left. The coefficients have to be multiplied on the left, and that's exactly what I did here. The B and the A came on the left. Okay. Now it so happens that for the free skew field, so this is always true, that the left row rank is equal to the right column rank. And so you can obviously define another kind of rank, which is the right row rank, which will equal the left column rank. And for a general skew field, these two notions might be different, but for the free skew field, they're the same. Okay? All right.
It's not the minimum number of rank 1 matrices if you add to every matrix, and there's no left or right.
It is.
It is.
But what's the left or right? I mean, you define a rank 1 matrix.
That's right. It might only work because it's the free skew field.
Yeah, in the free skew.
In the free
the
skew
free skew field is the same.
This is the same.
Otherwise, it may not be the same.
Otherwise, it might not be the same. Yeah. I think, I mean, what you can do is, yeah, that's. Okay. So I want to give a few examples. So that is one example where you took a linear matrix and its commutative rank and non-commutative rank were different. Okay. So I want to give you a few more examples, and maybe they light up something in your brain, or maybe they don't. But here's kind of what the phenomenon is. And I'm going to use A, B, C, D for the variables instead of T1, T2, T3, T4, because it gets easier. So here is one example, C, D, 0, 0. Okay. So that's a linear matrix, and its commutative rank is 3, and its non-commutative rank is 4. Okay. So far I have not really told you how one might actually compute the non-commutative rank. We know what the definition is, but it's not so clear how to compute it. But you should be able to compute the commutative rank of this. Yeah, and if you do, you should be able to see that it's 3 and not 4. Okay, it's not a hard computation, it's a 4 by 4 matrix. Another such example is again 4 by 4. So minus B, D, 0, 0, A, 0, minus C, D, D, 0, B. So even for this, the commutative rank is again 3 and the non-commutative rank is 4. Okay, so it's kind of subtle. It's not easy to spot immediately whether the non-commutative rank will actually jump or not. Yeah? Any questions so far? Okay. So here's where I'm going to digress a bit, and I'm going to talk a little bit about identity testing. So first I will live in the commutative world.
You can promise that you will eventually reveal how to compute non-commutative
Yes,
rank,
yes,
right?
yes. This is part of the first part of the talk, is how we're going to compute the non-commutative rank. Okay, but maybe let's also see why one might want to compute the non-commutative rank, and this is one reason why you might. And so I'm going to draw a parallel between the commutative world and the non-commutative world. Some of you may be familiar with this side of the story. So in the commutative world, you have what are called polynomial identity testing problems, which is, maybe somebody gives you something that looks like this and asks you, is this 0 or not? Okay? I don't want to be too rigorous about how exactly this is given. This is given as some circuit or formula or whatever, and asks you whether it computes the 0 polynomial or not. And how might you do it? Most naively, forget about efficiency. Just expand it all out and see that every monomial has coefficient 0. Okay, so there exists a naive algorithm. Okay. Now, what does this have to do with linear matrices? Is if I give you any polynomial, you can construct a linear matrix so that the determinant of this linear matrix is your original polynomial. Okay, and this is a construction that goes back to Valiant. Okay, so I got that right. And if I understand this correctly, and I'm not a great expert on this, this is really the beginning of VP versus VNP. Yeah? So this is really the beginning of VP versus VNP. This is also why determinant is BQP complete. And all of this are based on this construction. Okay? BQP? No, sorry, VQP. Yeah. It's not VP complete.
For formulas, so determinant is complete for formulas.
What is BQ?
Quasi-polynomial, no?
Oh, quasi. It's not quantum.
Yeah, not quantum. Anyway, but the point is, this polynomial is not the 0 polynomial if and only if the commutative rank of this guy is full. Right? That's what it means for the determinant to be non-zero. Okay? So the commutative rank of a linear matrix is a non-trivial problem. Why do we know this? We somehow know that if you can give a polynomial time algorithm for PIT, then this would imply roughly that VP not equal to VNP. Okay, and I say roughly because I don't actually know what the right precise term is. Okay. In the non-commutative world,
For people who've never seen it, you should notice that an algorithm implies a lower bound. This is one of the weirdest things about this. And you can say this is Cabanets and Impagliazzo.
okay, this is Cabanets and Impagliazzo. Okay. Now let's go to the non-commutative world, and it looks much stranger. So now I can ask you. Okay, so in this case, I just restricted myself to polynomials, but you can do this for rational functions, and there's a simple reduction that gets rid of rational functions. So in the non-commutative world, I can give you something that looks like this. And ask you, is this equal to 0 or not? Okay. Now you're inside a free skew field where x and y are the variables, and the ground field is some field. Okay, and now I ask, how do you even try this? Like, is there even a naive algorithm? Okay, and there's kind of troublesome stuff here. Like, you have a nested inverse. So in the polynomial, you kind of just said, okay, everything has to be some coefficient in monomial. So we will just take the coefficients of each monomial and check that they're all going to go to 0. But in this case, it just seems like there is no naive algorithm. Okay, so here's a question that I ask. Is there a naive algorithm?
I see. I would like to clear denominators by multiplying by one thing, but that one thing won't cancel everything out.
Exactly.
Right.
Yeah, you can't do it. I mean, if you want to clear, it's very hard. You might have other things too. You might have a left inverse and a right inverse, and you wouldn't know which.
Left inverse may not be
No, left inverse will be right
right,
inverse.
okay.
But you might have things like
You multiply the left
P inverse, Q, R inverse, and then you don't know what clearing denominators means. Okay, so I actually don't know if there is a naive algorithm. I wish to know. And so if you can think of a naive algorithm, independent of how efficient it is, I would be interested in resolving this. So this should follow simply from like associativity of and multiplying something by its inverse is 0 is 1. These just basic formal rules. It should follow from that. In fact, this one does, but it takes a bit of work to do it.
Wait, this is an equality?
This is an equality.
Whoa.
Okay, so this is an equality, and
Now, what can you deduce, if anything, from specializing, say, to matrices? You can, since matrices is
Yep.
sort of like the generic
Yep.
non-commutative.
you've gotten to the heart of the talk.
Right, okay.
So we will get there in not too long. Okay, so you have the same kind of procedure here. You can take a rational expression, and you can create a linear matrix in somewhat similar way. And the point is going to be that this rational expression is non-zero if and only if the non-commutative rank is full. Okay? And I'm not going to give you this procedure, but let me just give you an example. So suppose your rational expression was the commutator of B and A, then this linear matrix would be the one that we've been doing from the beginning. Okay? So whatever rational expression I give you, you can somehow concoct a linear matrix, so that when you Gaussian eliminate those kind of transformations, you end up with your rational expression at the end. Okay? This is a procedure, and you can tell me, like, it's kind of an inductive procedure. So you tell me what to do for smaller things, you tell me what to do for an addition gate, you tell me what to do for a multiplication gate, and then you just create.
So you need variance result and then more.
Yeah, I mean, variance is commutative, this is non-commutative.
I don't understand. Could you say again what thing on the left is?
This one?
Yeah.
It's the commutator of B and A, which is B times A minus A times B. Yeah? Okay.
In general, on the left is some expression
Involving additions, multiplications, subtractions, inverses, and without telling me, I mean the inverse, yeah. I mean some expression that looks like this.
So you got rid of all the inverses, went to the matrix.
Yes, it becomes a linear matrix, yes. But the inverses can show up when you do Gaussian elimination, right? So part of Gaussian elimination, and it's kind of hidden in this one, is you find a non-zero entry, and then you should scale it to 1 before you remove everything in the column and the row. And that scaling to 1 is the taking inverse. I will show. Okay? So this is the reason why we want to compute commutative rank and non-commutative rank, is to be able to solve these kind of identity testing problems. This is one reason to compute it.
Can you, for the sake of the video, write valiant next to this reduction and con next to this reduction?
Okay. Valiant. Con.
So non-commutative rank, you see that it's full, there's a notion of non-commutative determinant, which has to be...
Yeah. No. That's the problem. We have to get around this somehow.
There is a notion. It's called
There is a
quantitative
notion.
determinant, but,
It's just,
it's a different story.
yeah.
There's an interesting historical comment. Con's result came before Valiant's result, of course. Valiant didn't know about it, and it implies Valiant's result.
Yes, because you take a non-commutative, you take a polynomial, interpret it as a non-commutative polynomial, and you do it.
And the proof underlying it would be the same if you strip away the...
I mean, it's kind of a procedure, so there's not really a proof here.
But yeah, it's basically it's the same idea. It's just more complicated in the non-commutative case.
Yeah. Okay. So now let's talk a little bit about how one might compute the commutative rank in practice. So I have a linear matrix. So let's just take that same one for to keep in mind. And I'm giving you a lemma which says that to get the commutative rank of L, I can look at the rank when I plug in values for T1 and T2, and I take the maximum. Okay, and this has not a hard proof, And the proof is kind of goes by minors. Okay, so this is the definition of commutative rank. So which is going to be the size of largest non-zero minor. Right? And this non-zero minor is a polynomial because the entries of L are linear functions. So you take a minor, it could be a polynomial. So this guy is a polynomial in these two variables. And if this is non-zero, if and only if you can find some numbers to plug in to get a non-zero thing, right? This is where I need the fact that my field is infinite. Yeah. Once you have an infinite field, a polynomial being non-zero is the same thing as being able to find some numbers to plug in so that you get something non-zero. For finite fields, you can have like x to the p minus x and so on. Okay. But then once you have this, well, this is the size of. This shows that the rank of LAB is. Yeah. Does that make sense? Okay. So here's a randomized algorithm. Is to plug in random A and B and compute rank. See, computing the rank of a matrix whose entries are in the field, say the rational numbers or something, is simple. Right? Computing it symbolically where you have entries which are polynomials is hard because you have to decide whether a polynomial is 0 or not at some point. Right? So a randomized algorithm is you just plug in random numbers and with high probability you will be able to capture the rank. Right? If a minor is non-zero as a polynomial, with high probability it will turn out to be non-zero. So that's a randomized algorithm. It's a polynomial time randomized algorithm if you do it correctly. Now, okay, so we would like an algorithm that's polynomial time deterministic, but we got an algorithm that's randomized polynomial time. We still don't know how to get this. We're very far from that. It's okay. But now let's come to this side, the non-commutative rank, and we saw that there isn't a naive algorithm, right? But can we find some kind of randomized algorithm that's similar to this? And we had an idea shoot out from the audience. Is, well, in this case you were plugging in numbers because you were in the commutative setting. You have the non-commutative setting, so what should you plug in? What can you possibly plug in? Where do you possibly find something non-commutative? And we've all seen matrices in our lives, and we all know that matrices don't commute. So you should be able to plug in matrices to check. Okay, so a similar algorithm for non-commutative rank would be to plug in matrices, but of what size? Okay, it's kind of important. Is what size? So let me define a bunch of ranks. So I will define a rank for each integer d, which will be the maximum of rank of L of AB, where A and B are d by d matrices. Okay, so I plug in d by d matrices. So what does L of AB look like? Okay, and maybe there's a little bit of a style point here. The ones become identities, because that's what the identity in d by d matrices are. 0 minus identity minus A minus B. Okay, so
It's an ND by ND matrix.
that's right. So if the original matrix was n by n, this matrix is much larger. How much larger? It's d times larger. Okay, so it's n times d. So its rank would be much larger than n. But the fact that it's d times larger allows me the liberty to renormalize by d. Yeah, this is okay. So I will eventually renormalize by d, and let's see where I want to go. Maybe I go here. Okay. So the first thing I want to notice is the commutative rank is just rank 1 as I've defined it. 1 by 1 matrix. Okay. Then you have this rank 2 where you plug in 2 by 2 matrices and check. And I want to renormalize it by 2. Then I have this rank 3 and renormalize by 3 and so on. D. And I can keep doing this. And the claim is on the other end you have what's called non-commutative rank. Okay? So all these kind of renormalized ranks are interpolating between commutative rank and non-commutative rank. So I'm going to state this as a theorem. So the way I state this theorem is non-commutative rank is equal to the limit as d goes to infinity rank d over d, which is equal to the supremum of rank d over d, which is equal to the maximum of rank d over d. Okay, so let's just hold back a second and see if this is something we believe. Okay. Well, if I write something like this, it starts to make some kind of sense. But there's serious issues here that, if you look at it naively, there's serious issues here. First, the non-commutative rank is an integer by definition. Yeah? There's no reason none of these numbers have to be integers because you're dividing by something. And so why is any of these three things an integer? And also, why is lim equal to sup equal to max? Yeah, this is a bunch of slightly weird things going on here, and we need to know how to fix it. Okay, so I'm just going to say y lim equal to sup equal to max equal to integer. Okay, somehow all of them are actually question marks. You need to know something before you can say these things are the same. Yeah? Okay. So I finally come to the meat of the talk. And this is called the regularity lemma. Okay? So I'm going to spend the next few minutes, making sense of why all those things are equal. Okay? And basically the thing that drives pretty much everything in this particular story is the regularity lemma, which I'm going to abbreviate to RL. And
Has nothing to do with Guy's lecture.
okay. It's a simple statement. It says that rank d over d is an integer. Okay. So if you look at this, maybe a more complicated linear matrix in your head, and you plug in d by d matrices, the maximum possible rank you can possibly get with that is a multiple of d. It's a very strange condition, and there's no reason a priori why something like this you would expect.
You did this calculation. It feels like that. Does this reveal it?
Sorry?
Does this calculation
Yes.
reveal it? Yeah, okay, good.
Yes, this is, yes, it's hidden in here. In this particular case, okay. But a more general thing, you might come up with. So what do you know? You know that B comma A is non-zero for say 2 by 2 matrices. But if you want this to have full rank, you need B and A so that this thing is invertible.
Oh, right.
Yeah. Now you see where it comes from. Okay. So this is. So again, I have to put names. So this was discovered by Ivanios, Yuming Kiao, and Subramaniam in a way in which they made this kind of constructive. They said if you give me d by d matrices that you plug in and you get some rank, they will tell you how to modify these d by d matrices to jump up to the next multiple of d. Okay, so these guys have some kind of constructiveness.
This is extremely recent.
This was extremely recent, yes.
December
15.
2015.
Okay, But the claim is that this was already known to people like Amitsur, just in a different language, and they have no use for it. Okay? And so what is the idea? The idea is you plug in random d by d matrices into your linear matrix, and you just do Gaussian elimination. And do Gaussian elimination by blocks. Right? You kind of do, like if you think of this as a generic d by d matrix, you do Gaussian elimination by blocks. And then you come down to this one statement that is due to Amitsur. So Amitsur says this. Okay? So R is some rational expression, non-commutative, and you fix some integer d, some positive number d, greater equal 1. Then Amitsur says if R is not identically 0 on d by d matrices, so let's say R has some number of entries t1 to tm on d by d matrices.
Don't get too small with the.
Yes. If R is not identically 0 on d by d matrices, then R on generic ones, or random if you wish, is invertible. For random, generic, AI in d by d matrix. Okay. Some of you might recognize this as the problem that I threw in the bring your own problem session. Well, there I gave something slightly easier. I said take a polynomial, but it's actually true in this more generality. And this is what allows you to basically do Gaussian elimination blockwise. And if you do Gaussian elimination blockwise, what do you end up with? You'll end up with a bunch of identities, right? And each identity contributes d to the rank. Does that make sense?
How do these people do Gaussian elimination block?
They don't do it. Yeah.
They have some different?
They have a slightly different proof. And okay, so as far as I understand, they did not know this. Okay? They stumbled upon this proof because Ivanios thought that it should be hard to differentiate a full matrix algebra from a division algebra, and that gave him some root and helped to predict this. But the way they prove it is they work with division algebras that are not as general as this, but some just slightly bigger than the field F itself. And in these division algebras, they're actually able to work efficiently. Okay? But the reason it's true is this, but you can't make this constructive. Okay? Working with the free skew field in a constructive way is kind of hopeless.
And does that imply, does their result imply Amitsur theorem?
Yes, these are if and only ifs. And the reason they're if and only ifs is this construction.
So that is another proof of Amitsur's theorem.
Yes. Okay.
So in the language of matrices, if you think about this statement, the rank of this linear matrix, which is divisible by d, will be either full or be lesser.
Yeah, and that depends on whether it's 0 or not.
Well, I guess if it's 0, it will be either 0.
No, it will be d less than full. Okay,
but
yeah,
it's
something.
0 if it's identically 0.
Zero,
The
sure.
rank, so the rank is either 0 or n times d.
No, the rank is, I mean, it depends on when the rational expression breaks down.
Yeah.
Anyway. Okay, anyway, so this regularity lemma at least gets rid of this. Everything in the sequence is an integer. So max and supremum are the same, and they're both equal to the integer. Okay, so this is a kind of solved mystery. But now we have to somehow figure out why lim and why you get the limit. So you have to know something about how the sequence grows, and you might have a naive guess. The naive guess is that the sequence is monotone, but this is actually not true. Okay, so let's see where I want to go. So the naive guess is, of course, that if you want lim to be equal to supremum, maybe the sequence is monotone. This is not quite true, but it's essentially true. Okay, and wait a second, where am I? Okay, so the lemma is that this sequence is increasing once d is greater than or equal to, say, n. Okay, and this has kind of a simple proof, and you will see why the regularity lemma is key to everything here. Here's the thing. So so let's say the rank of d over d is k.
You want to say it's your fault.
Sorry?
You want to say that this lemma is yours.
No, this lemma is
That's actually-
is an IQS. Yeah, what I can do is I can do this, but whatever. So, right. So you took the rank d over d and it's k. It has some rank, it's some integer. Now what does this mean? This means that rank of d is d times k. So rank of d plus 1 is at least d times k, right? Because you can just pad the matrices with zeros and you won't get something better. But then I claim d times k is greater than d plus 1 times k minus 1 under this assumption. Because k, so d will be greater than or equal to n, which will be greater than or equal to k. And under that assumption, I claim this is true. Once you have this is true, this means that the d plus 1 rank over d plus 1 is greater than k minus 1. And that implies by the regularity lemma that it's greater than or equal to k. Okay, so without the regularity lemma, you can't even prove something like this. Just kind of strange that you can't. Okay, so that's the warning. The warning is this is only true once you take d to be greater than or equal to n, or with some tricks you can get it down there. But it's not true for small values of d. Okay, so it's kind of funny. This sequence can jump up and down a bit, and then eventually has to be reasonable. Okay. Yeah, and let me also mention that this one is false. Okay, so it's true for an infinite field, as stated. So if I relax the condition of infinite field to a large enough field, it will remain true, because the only thing driving it is the fact that a polynomial is non-zero if and only if you can evaluate it at some point. So if you have a large enough field, it's okay. But there's no reason, that's a priori not a reason for it to be false when the field is small, but it is false if the field is small. Field is too small. Okay, so these are the two things that I might talk about if we have time.
Lemma still doesn't prove that.
Yes, correct. I was trying to run away. So this lemma plus the fact that rank of 2d over 2d will be greater than or equal to rank d over d. Yeah, because if whatever d by d matrices you had to get a certain rank, you can take the direct sum of two of them, and those will be 2d by 2d and be normalized. Okay, so this plus that will. That's great. So this is also solved.
What field size is this?
What field size?
Yeah,
For the counter example, or
yeah.
I think it's like d less than no. The field size should be less than like log base d of n or something. That's the example I have, but
But the proofs that it works only happens at
the proof that it works requires like the field size to be greater than like d times n or something, roughly. Don't catch me. Okay. Okay. Here's now where I come to. Okay. So here's the theorem. The theorem is actually that the non-commutative rank is equal to one of these numbers as long as d is greater or equal n minus 1. Okay? You got to compare it with that.
So it stops increasing.
So once it gets to n, it doesn't increase, it's just constant. Okay, so this is a theorem of Dirksen and myself, and has a very small proof, but maybe the proof that I give you is for n plus 1. Okay, and I give it to you in this one example. So, so before I give you the proof, let me tell you what the key lemma is. The key lemma is to kind of do that upward lemma backwards. So what did I do? I said, look, you have some rank d over d is some number. Then when you go one up, it's at least as much as k. I'm going to go back. So the key lemma is going to be that if rank of d plus 1 over d plus 1 is equal to n, is full, that means that rank of d over d is also full if d is greater or equal to n plus 1. Okay? Let's see. I will do it in this case, and I will give it to you in numbers. So let's say you had some d plus 1 by d plus 1 matrices so that this is invertible. Right? So for the sake, let me just take d to be 1,000 or maybe 999. So these are 1,000 by 1,000 matrices that you've plugged in. So this is a 3,000 by 3,000 matrix, and it has full rank. Now, okay, so you have these blocks. Now from each one of these matrices, I remove the last column and the last row. Okay, so I remove this column, this column, this column, that column, that column, that column. So in doing so, what have I done? I've taken each of these A, B, A and B, and I've removed the last row and last column. So now there are 999 by 999 matrices. Well, I got this from a full rank matrix by removing 3 rows and 3 columns. So its rank is at least 2,994. Yeah?
97. Oh, wait, sorry.
Yeah? So at least 2,994. So, so I knew that rank of rank 1,000 was 3,000. So because of this, I know that rank 999 is greater or equal to 2,994. But it must be a multiple of 999, right? Yeah. So by the regularity lemma, this means rank 999 is greater or equal to 997, which means rank 999 over 999 is full. Okay. That same argument when you plug in d and n, you will get it. And to go to n minus 1, you need a little bit more tricks. Okay. So if we come down here, back to this computation, so you have the commutative rank, you have something funny going on up till, something funny goes on here, and then all of this is equal.
You didn't prove that it's equal to the non-commutative rank, because you proved that it stabilizes, but you didn't prove that it's
Yeah, okay, I didn't prove that it's equal to.
the definition of non-commutative rank is
Right.
not given.
Yes. Okay, so what Avi's claiming is I've proved all of these, and I've told you how to compute all of these, and I've ignored the fact of how to equate it to the non-commutative rank, and maybe I will continue to ignore it, but one way to construct this skew field is through such a procedure, where you create these division algebras coming out of d by d matrices, and you take some kind of weird limit. Okay, so this part is so this part again I attribute to Amit Sur, which is also why it's a mystery how they got there without knowing this. I don't understand, because you need this to construct this. Yeah, anyway. Okay, so let's see what else I have before.
The lemma from the theorem is about the full rank, and the full was used in order to make 2994 into 2997, and not 4 times that. Not to jump too high.
Sorry, what?
No, in the lemma you used, it was about full rank.
Yeah, I don't think it really matters.
But I see, and then that's how the.
You could still take k and k and.
So the lemma implies the theorem almost.
Yeah, the lemma implies the theorem is kind of silly. Yeah, I mean, that's right. The lemma implies the theorem
Right.
in a straightforward way.
Right, good. But to prove the lemma, you need it to be full, just because you didn't want the ranks to jump. Right? Because I have 999 plus
That's right. Yeah. Okay. So I mean, the way to say it would be like, is greater or equal k? Yeah, but
okay, so
but we only want.
yeah.
Yeah. Anyway, that's right. Yeah. Okay. Greater or equal k is greater.
And so this gives you now a way of computing the non-commutative rank because you can stop at n.
Absolutely. So here's a randomized algorithm, right? So randomized algorithm is to plug in random n by n matrices, let's say. Okay? Well, it's kind of strange because earlier we had no idea what the size of matrices to plug in, and now it just turns out to be pretty small. Okay? Now there are deterministic algorithms. And I won't go into these. So the deterministic algorithms, there is one that Avi and his collaborators have that works over characteristic 0 using operator scaling. It turns out to be an equivalent problem. And these same people, Ivanios, Kyao, and Subramaniam, also have a deterministic algorithm for every field that's large enough for.
What do you mean deterministic algorithm?
Meaning they can actually find an n by n matrix, that n by n matrices to plug in to verify that the non-commutative rank is full.
We don't know for commutative rank.
We don't know for commutative rank.
Why can you do it for non-commutative?
That's right. This is the strangest thing ever. Is you can't do it for commutative rank, but you can somehow do it for non-commutative rank because.
When does it imply that?
No. Yes, it's the other way. So if you could do it for commutative rank, you could do it for non-commutative rank, but not the other way around. Yeah, it's a little bit strange, but I'm not going to get into it. I will leave this there.
It's the other way around.
Okay, so before we get to the break, maybe is the time to say a few things that you can forget after the break. And here's where I want to connect it a bit to a bunch of other ways of looking at non-commutative rank and where it shows up. So the first thing I want to say is, let me take a linear matrix that looks like this, and then let me change bases. So suppose I took, P and Q, which have different, invertible matrices, and I just changed the basis of each one of these xi's. Okay, so P and Q are in GLN, let's say. Okay, then I claim the following is true: the commutative rank of L is the commutative rank of L tilde. Okay, I also claim the non-commutative rank of L is the non-commutative rank of L tilde. But I also claim that even the D, these D ranks that we define are the same whether you pick L or L tilde. Is this believable? It's believable, right? Because nowhere did I actually really bother too much with the basis. Yeah? If you plugged in A1 to AM here, you can plug in the same A1 to AM here and the rank won't change. It will be just a basis change matrix. Yes. Okay. So what does this mean? This means that, whatever this commutative rank and the non-commutative rank and the rank T, they're all properties of just this tuple. Okay? But they're all properties of this tuple up to an action. Okay? So all properties of this up to GLN cross GLN action. Does that make sense? There's a bunch of numbers that you have, and they're invariant which point in this orbit you take. Okay? So maybe I will be a little silly, and I will take SLN instead of GLN on both sides. This is kind of a little bit of funniness. And the claim is, so I will call this point X. So L has full non-commutative rank if and only if 0 is not in the closure of the orbit with SLN cross SLN. Okay? So it means take this tuple of matrices, apply SLN transformations on both sides, see all possible tuples you can get, and then take its closure, limit points if you're complex numbers, yeah, and whether it contains 0 or not will tell you whether you have full non-commutative rank or not. Okay, so this is same thing as saying by definition that X is not in the null cone for left-right action. Okay, it's called the left-right action because one's acting on the left and one's acting on the right. Just a name. Okay, so I want to do one example.
This already is elementary definition of non-commutative rank.
This is an elementary definition.
In the sense it doesn't require a definition of the free skew field.
Well, but then we go back to the point where we equate it to the lim and sup and max, but we
it's full rank. Yeah, you still call it full. Good. Yeah.
okay. So I want to just do an example of something like this. So let me take a linear matrix that looks like T1, T2, T3, T4, T5, and a big block of zeros. And I say big block because it's 2 by 2, and 2 plus 2 is greater than 3. Okay. Now, first of all, the commutative rank of this is 0. Sorry, commutative rank of this is less than 3. Yeah, this is just too big a block for you to be able to get any of the permutations to be non-zero and compute in the determinant, right? So, commutative rank is less than 3. But I also claim, for kind of the same reason, the non-commutative rank is less than 3. Okay, and what's one way to see this is, let's look at this. This can contribute, let's say we're looking at the column rank in this non-commutative field. This can contribute 1 because it's one row. This can also contribute only 1 because it's one column. So the non-commutative rank also cannot be greater than 2. Okay, so the non-commutative rank is also greater than 3. And which means the same argument exists for whatever. You do this, you know, if you can get your linear matrix like this, I and j, with I plus j greater than n, then non-commutative rank is less than full, less than n. Okay, and it's a if and only if up to change of basis. Okay, so by up to change of basis, I mean if you can find some basis, you know, some basis change p and q, so that your entire linear matrix lives inside this kind of a picture with a big block of zeros, then your non-commutative rank will fall. Okay, and one way to test that is try doing it for this one. Okay, you will not be able to change basis here to be able to get it in this kind of a form where you have a big block of zeros. Okay, but it's kind of hard to say you can't do it. You can't prove it. You can keep trying and trying and trying, and you won't be able to do it. And that's the reason this has full non-commutative rank. That's one way to do it. Okay.
Can you show us how to get 0 in the, or say the closure of this one?
But 0 is not in the closure of this one.
Yeah.
Oh, sorry, right. Good.
Yeah, but I can show you how to get 0 in the closure of this one.
This also a theorem of Cone.
Which one?
The null cone theorem.
I think that's a theorem of King, but maybe I haven't read what Kohn wrote. Yeah, I thought it was a theorem of King. So I define a matrix A lambda, which is lambda square, lambda inverse, lambda inverse. This is inside SLN, right? What's lambda? Some non-zero number. So if I multiply this with something that looks like this, and then also multiply on the right side by the same one. Okay, what I'm going to end up with is the first thing in there gets multiplied by lambda to the 4. This one gets multiplied by lambda squared and a lambda inverse. So that's a lambda star. And the same thing is going to happen here. And the things inside which were zeros, and I'm going to keep it as zeros, but I'm going to tell you what they would be multiplied by. They would have all been multiplied by lambda to the minus 2. Yeah, and that corresponds to this lambda inverse and this lambda inverse. Right? But because they were 0, they stay 0. Now what did you do? You took this matrix and you could scale it with some powers of lambdas, positive powers, and now you can take lambda going to 0. Okay, so you take lambda going to 0, and this thing will go down to 0. Yeah, okay, that's the thing. So maybe this is the right time to take a break, and then I'll come back and refresh all the equivalent definitions, and we'll go from there. In some sense, this is a summary of the first part of the talk. Is you have a linear matrix, and then I have the tuple of matrices. It's just my, and I'm giving you many equivalent conditions for non-commutative rank. Okay, so the first one is just that it has full non-commutative rank. It's the same thing as you're able to plug in n by n matrices to get something invertible, which is the same thing as it's not in the null cone for the left-right action. So 0 is not in the orbit closure, which is the same thing as you cannot write all the xi in this form with a big block of zeros. And this one, I just want to put it in a basis independent fashion, which is to say that there is no shrunk subspace. Okay, so this is kind of a shrunk subspace because something large here is getting shrunk to something small here, and that cannot happen, right? If you have full non-commutative, that cannot happen. So the way to say it is, for all subspaces of the source, you think of these matrices as linear transformations.
K is F.
Yeah, that's right. I knew this would happen. Okay, so for all subspaces in the source, you look at the image under all the xi's, and the span of that image should be strictly larger than the subspace you started with. No, not strictly large, at least as big. Yeah, it cannot shrink it. It has to be at least equal to or bigger. And then there's this one. This only works in characteristic 0. Is given this linear matrix, you can define a completely positive operator on positive semi-definite matrices, and it takes a positive semi-definite matrix to sum of xi p xi conjugate transpose dagger, is that what we call it? Dagger, adjoint. Yeah, they all mean the same thing to me. Anyway, so you have this operator, and the fact that L has full non-commutative rank means that this operator will not decrease the rank of any positive semi-definite matrix. Okay, and this is the approach that operator scaling comes out of. Starting with Gurwitz. Yeah, maybe Gurwitz did not actually know the connection to this. Yeah, so this part of the theory developed independently, and then at some point the two merged in not too recent history. No, in recent history.
Is one direction of this clear?
Neither direction is clear to me, but
No, but between 5 and 6, the direction is elementary and simple.
is it? I see. Okay.
Yeah.
Yeah.
Basically, the PSD, the matrix that will shrink the rank is a projection matrix on the subspace V. That is what.
Okay.
Very simple.
Yeah. All right. So now that I've given you like several points of view, I will make another point of view, one which doesn't talk about linear matrices but talks about linear subspaces of matrices. Okay, so I use a script X or calligraphic X, whatever, to denote a linear subspace of matrices. Okay, so what do I mean by linear subspace? N by n matrices over the field, it forms a vector space, and I'm just looking at a linear subspace of it as a vector space. Okay? And corresponding to such a linear subspace, I can define a rank, and it's going to be the maximum of an element in this linear subspace. The maximum possible rank over all elements in this subspace. Yeah, and this should remind you of the first lemma that I proved about the commutative rank of a linear matrix. How you can get it by evaluating it at different points. Okay, and I will also define what's called the blow up of the space, which is okay. So I have two ways to write it. So the first is you take sum of xi, sum of ai tensor bi. The AIs come from the subspace, and the BIs are just any n d by d matrices you like. Okay, and this is a subspace of dn by dn matrices. Now let me be a little clearer here. What do I mean by this tensor product? So I mean the Kronecker product. P tensor Q is P11Q, P12Q, P1NQ, Pn1Q, Pnq. So it's a block matrix. The blocks are all going to be some scaling of Q, and that scaling is given by the entries of P. Okay, so if this is n, so these are n by n matrices, these are d by d matrices, so the tensor product is dn by dn matrices, and then you add a bunch of them. That's how you make sure it's a linear subspace. Okay, so what I want to do is I want to now take this subspace point of view and connect it back to linear matrices. So if you have a linear matrix x0 plus t1 x1 plus tm xn, and then you can take, corresponding to this, the span of the matrices. Okay, these are inside n by n. And my first lemma is going to be that the commutative rank of L is going to be the rank of the subspace. Okay, you would not have questioned me if I put T0 here, then it would be clear that it corresponds exactly to this. But even if I don't put the T0 there, it's the same. Okay, this is kind of a simple proof. So first let me prove one direction, which is this way. So to show that the commutative rank of L is smaller than the rank of X, all I say is commutative rank of L is the maximum possible you get by plugging in numbers for the TIs, right? So whenever you plug in such a number, you get an element of X, of this subspace. Therefore, the maximum rank here is smaller than the maximum rank here. So this is okay. For the other direction, let's say you started with something of maximum rank here. So that thing of maximum rank is going to look like this. Now if A0 is non-zero, you can scale it to 1, right? So if A0 is not equal to 0, then this guy here is equal to A0 times L of A1 over A0 blah 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 AM over A0. So it has the same rank as this guy. It's fine. Now what do you do if A0 is equal to 0? Then just perturb it a little bit and you can't drop the rank. Yeah, if A0 is equal to 0, perturb a little bit and rank can't fall. This is a fairly simple argument. Okay, it's kind of standard. Anyway, I'm going to leave it there. And now in the same kind of I want to say the rank D of L is the rank of this blow up. Okay, maybe I didn't write the word blow up there. Maybe I should write it here. This is called the dth blow up. Okay, and do you see why? It's maybe not so clear, but plugging in corresponds to taking the tensor product. So let me do this example here. So if you remember the first example that we have, L of AB was 0, identity, A, B, 0, minus identity, minus A, minus B. Right? And what was X naught? X naught was going to be 1 minus 1. X2 was going to be 1 minus 1. And X3 is 1 minus 1. And X naught tensor A plus X1 tensor B plus X3 tensor, X1 tensor identity plus X1 tensor A plus X2 tensor B. This expression, if you plug it in, you get that. Okay? It's just kind of another way of writing it. So we have this. So what did I want to do? So what this means in particular is that non-commutative rank of L is equal to limit or max or supremum of D of the rank of this blow up divided by D. Okay? So if you wish to talk about subspaces of matrices instead of linear matrices, you could have done that. Okay, so with this, I want to move to tensor rank lower bounds. Okay. So first I want to tell you one kind of procedure that you can use to prove lower bounds on tensor rank. Okay, and this is okay, but I will only stick to 3 tensors. So FM tensor, FM tensor, FM. And to prove a lower bound, let me just hold on. Everybody knows the definition of tensor rank? Yeah? Okay, let me do this. So a rank 1 tensor or simple tensor is something of the form V tensor W tensor Z. Yeah? And for any tensor, its tensor rank is the minimum number of simple tensors that you can write it as. Maybe I put R, T1 to TR, TI simple. Yeah? Okay. And if you had only 2 factors, that would be matrix rank. Okay. So here's how to prove lower bounds. Is you start with a map which is linear into matrices. I want to call my map phi. Okay, into some large D by D matrices. Okay, and under this map, suppose all the simple tensors go to rank less equal A matrices. Yeah, is that clear? This is a map that has the property that every simple tensor goes to a matrix whose rank is less equal A. Then I claim the tensor rank of anything, any tensor in here, will be greater or equal the rank of the matrix that it goes to divided by A. This follows because tensor rank is subadditive. Sorry, because matrix rank and tensor rank are both subadditive. Is everybody? Yeah. Okay. So we got this. Now what I want to say is, how do you find useful linear maps that give this for you? Right? There are some that you can do. You can just say, well, collect these two into something, and so it become okay. Maybe I don't even need D, E, maybe DE. Doesn't matter that they're the same size. Okay, so you club two of the factors, and you get a linear map. So a silly one is to take FM, tensor FM, tensor FM. Club these two factors, so you get a map from this into FM tensor FM squared. Yeah, these you can think of as M by M squared matrices, and if you use this map, the best lower bound you'll ever be able to prove is going to be M, because every simple guy goes to a rank 1 matrix. A tensor B tensor C goes to A tensor B tensor C, so it's a rank 1 guy here, but the largest possible rank of any matrix here is M. So the best lower bound you'll ever be able to prove is M. Okay, so I ask again, where do we find matrices that give us
Maps.
Sorry, where do we find maps? Where do we find linear maps that give us better lower bounds? Okay, and the idea is one can take advantage of non-commutative rank to get lower bounds that are better than this. Okay, or rather, one can take advantage of blowups. So here's what I want to write. I want to write using blowups. I will get special kinds of. I will give you a collection of I will give you linear maps coming out of this idea of blowups, and here's the idea. So let's say you have a linear subspace which is the span of x1 to xm. Okay, then you can think of this. From this you can get a linear map from Fm to n by n matrices, which sends like C1 to Cm goes to sum of Ci xi. Okay, so this linear space is being parameterized by this guy, so that the image of G is precisely that linear subspace. Yeah, it's clear? The image is precisely that. So given such a linear subspace, I want to create a map from this. So phi will be a composite map, but I will tell you what each step is. The first step is G tensor identity. So I apply G on the first factor, and the second factor I will just take identity, but I interpret this as M by M matrices now. Okay, so G will land this guy into N by N matrices, and this one just becomes M by M matrices, and then I take Kronecker product, that Kronecker product, and I get a map into Nm by Nm matrices. Yeah, this is clear. Now where does the simple one go to? Okay, so V tensor, W tensor, Z. So this is a simple tensor. So the V goes to G of V, tensor W tensor Z. Yeah, this is a rank 1 matrix. This has rank less equal the rank of this linear subspace, because G of V is an element of this linear subspace. And when you take the Kronecker product of matrices, the rank is multiplicative. So that means the simple guy goes to something whose rank is less equal the rank of this linear subspace. Okay? But on the other hand, what is the image of this map? Okay? So I take phi. What does phi do? It does nothing to this, and it takes the first f to the m and gives me the linear subspace, gives me this linear subspace, right? So the image will take this, and I will get this guy. And what is the image here? This will almost by definition be the dth blow up. Okay? So that's another way to write this guy that I sort of forgot. So another way to write this guy is it's the tensor product of this and d by d matrices. Okay? So the image of phi is the dth blow up. So what's the best possible rank you can get? Best possible lower bound you can get?
Max rank of X, which is a rank.
Yep. Best possible lower bounds are going to be the rank of this guy, of this blow up, but you divide by the rank of the original subspace. Yeah. So if you can find yourself a blow up which has significantly larger rank than you expect, that would give you good lower bounds. Does that make sense? Okay. Now, let's see. This is the blow up rank of D. We know that over D is going to be less than or equal to the non-commutative rank. Okay. Maybe I didn't define non-commutative rank for the linear subspaces, but you can create the linear matrix and take its non-commutative rank, and it's be the same definition. So that means this is less equal D times that. So this best lower bound that you can prove is going to be less than D times. Wait, why did I get D? There should be an M. Yeah, the mth blow up. Sorry. M.
And also in the image over there.
M times the non-commutative rank divided by the commutative rank. Okay, so it's kind of a special set of maps. It's not the most general setting that you can think of, but it seems to be one general setting where if you could somehow get a large ratio of non-commutative rank to commutative rank, you would be able to prove lower bounds better than M by whatever that factor is. Okay. So at least we know cases where this is greater than 1, right? Yeah, so maybe we can do better than this guy.
So
But
that's 3 over 2, right?
Yeah.
yes, you can do 3 over 2. But it's still linear. You can do 3 over 2m. You can't do far better than that. Okay, let me see what I am. So now I want to talk basically about this ratio of non-commutative rank to commutative rank. Okay, so
So,
yeah,
so, but we also have to give it to give something explicitly, which we haven't talked about.
yeah, that's right.
Right. But what we would have to do is we would have to find a particular entry of element of X,
Yes.
which has this high non-commutative rank.
Yeah, I mean you have to somehow find this the rank of this blow-up, right?
Right.
You have to give a lower bound for the rank of this blow-up. So you have to find an explicit matrix in here that has high rank and so on. Yeah,
We
so
already know how to do it with 3 over 2.
for 3 over 2, yes, yeah.
Right, 3 over 2 we know how to do it. We're already at m equal to 2.
Yes. Yeah. In fact, I will tell you what the matrices here are. The matrices here would be, say, 2 by 2, for example, and B to be, and the commutator would be maybe 1 minus 1 or the other way around. I can't remember.
Okay. Oh, I see 2 non-commutating whose commutator is invertible.
So in practice, we actually know how to do this. anyway. Okay, so I want to concentrate on examples where this ratio is large. Talk about how big or how small, how big can this ratio actually get? And can we actually reach whatever upper bound we prove on it? So the first theorem, and this is due to Flanders mostly, is that the ratio is at most 2. Okay, so this is kind of a.
It will not lead to impressive tensor rank lower bound.
Sorry?
This method will not lead to impressive tensor
Yes.
rank lower
So this already tells you that the best possible lower bounds you could have proved using this kind of method is 2 times m, which if you have seen in other places is basically where we're stuck. Yeah. So the proof of this is kind of elementary. So I'm going to do this in terms of linear subspaces. So take some matrix in this linear subspace whose rank is equal to the okay, when I write commutative rank of the linear subspace, I just mean its rank. Okay, so I can find some matrix with the largest possible rank. Now in some basis, this matrix A is going to be a bunch of 1s and zeros everywhere else. Yeah. When I say in some basis, I mean I allow you left and right basis change, which is basically row. This is what row reduced echelon form, or maybe row column reduced echelon, whatever it is. Okay. So you can make A into this form.
Put zeros where you want.
Put zeros everywhere else. Okay. Once you do this, so in some basis. So in this basis, I claim all B in X must also be of this form. Okay, this is of size R. Let's call this rank R. So it's R and R. Okay, and the reason is, suppose some other matrix in this linear span had something non-zero in this bottom right corner, then you can take a linear combination of A and B and you will get something of slightly larger rank. Okay, it's a very simple exercise to prove. You can just make sure that this plus some other row and column will give you a larger non-trivial minor. Okay, so that means all of these must be inside something like this, R, R. And if you remember, we made this I kind of made the same argument back when I talked about this big block of zeros and I and j and why the commutative rank must be less than n. It's the same reason. So now if you maybe make the linear matrix or whatever you want, these columns can contribute at most r to the non-commutative rank. These rows can contribute at most r to the non-commutative rank. So the non-commutative rank can at most be 2 times r. Okay, that implies the non-commutative rank is less than or equal to 2 times r. Okay, that's the theorem. Yeah, it's kind of sad, but we knew how to make use of it, but we can't make too much use of it. But now let me also show you that this ratio is actually tight. So we know an example where this ratio is 3/2. Yeah, but I can actually make this ratio more or less tight. Okay, so first of all, you can't reach 2. It will always be less than 2. It's kind of an inductive argument, starting from 1 by 1, and you can do it. So now I want to reach 2. So I can give this construction, and I will write it in 2 ways. The first way will be extremely elementary, but it's very hard to see why it must work. And then I will tell you why it works. So here's the construction. First, everyone's familiar with this notation? 1 to q. Yeah, just numbers 1 to q. So the set A is going to be subsets of 2p plus 1 of size p. Is that also familiar notation, or did I make it up?
No.
It's familiar?
All subsets of.
Yeah, it's all subsets of numbers 1 to 2p plus 1 of size p. and B is going to be all subsets of numbers 2p plus 1 of size p plus 1. Okay, and the claim is the cardinality of A and B are both the same is equal to 2p plus 1 choose p. Okay, that's good. So when I write FA, I mean a vector space with basis E sub I in A. Yeah, so I don't know how to write this. Okay, it's a formal vector space of this dimension, and I'm going to label the basis vectors with elements of A. Yeah, every subset. Now, for all I,
You may want to say these are just the two middle layers of the Boolean cube. A and B are just the two middle layers of the Boolean cube.
yeah, okay. I don't know what exactly that means, but I believe it.
Subsets of roughly of roughly half the size of
Yes, yeah, okay. So I'm going to define a bunch of matrices, and it's going to look funny. So the way I define a matrices is I tell you how it goes as a linear transformation from this vector space to the vector space that's labeled by p plus 1 subsets. Yeah, and it's going to do this funny thing. It's going to do, so it's enough to tell you where each of the basis elements go, and it goes to I union I if I is already not in I, and the number of j less than I, j in I, is odd. Okay, and
the number of things should be outside the graph.
yes, the number should be outside.
Maybe you put that down.
Yeah. Cardinal, yeah, anyway, whatever. Minus of the same thing if I is not in I, and the same thing, but if the number of thing is even, and 0 if I is in I. Yeah, it's kind of a strange set of matrices that I created out of nowhere. Yeah, that's it. So where do I go? Where do I go?
But maybe it's a good comment to say that if P is 1,
Yes, I was going there
oh, okay, sorry.
eventually, but yeah, if P is 1, see if you can spot it. It's not. Yeah, I mean,
Your example.
if interpreted in the right way.
Those three matrices that you have.
Yeah, but maybe not in the same basis. Maybe you have to put a sign to some of the bases and reorder them. Okay, so I take the subspace, which is generated by all of these guys, x1 to x2p plus 1. It's a subspace of this big number. And the claim is that the non-commutative rank over the commutative rank is getting close to 2. But okay, so the non-commutative rank is full. That's the first claim. The commutative rank is 2p choose p, which is equal to the rank of every non-zero matrix in this linear subspace. Okay. One of the claims is that every matrix in this linear subspace, which is non-zero, has the same rank, and that rank is equal to this. Okay. That already tells you there's a symmetry somewhere, and therefore you should expect a group somewhere. And this number, by the way, is 2 minus 1 over p plus 1. Okay, so this approaches 2 as p goes to infinity. Okay. Now here's the little tidbit of what these matrices are. And if you don't know this, it's okay. Doesn't matter so much. Is this f to the a is this exterior power, is the pth exterior power, and f to the b you identify with the p plus first exterior power, which if you don't know, forget about it. I won't say too much about it. And xi is the map that goes from this, which takes something in here and wedges it with ei. Okay, so if you know it, you know it. If you don't know it, you don't care. But this is one description that's basically kind of basis independent, and therefore you get some of these. For others, you have to work a little harder. Right.
So you're not proving these properties?
I will not prove this. Yeah, it's so actually, this is where your comment comes necessary. Is to prove that the non-commutative rank is full, you have to find matrices that you plug in to get some big thing invertible. This seems to be basically the only way to do it. Okay, and it's actually kind of not so. So if A1 is okay, so I have a 1 just in that corner. A2 is a 1 1. A3 is 1 1 1. Blah blah blah. And these are of size p plus 1 by p plus 1. And then you take a x1 tensor A1 plus x2 tensor A2 and so on. You get something invertible. It's not the easiest thing to prove, but I have an extremely elementary proof of it, where I compute the determinant. Okay, but surprisingly hard. Anyway, what was I going to say? Now, when p is equal to 1, it's that example from the beginning. It's that example where x1 is something like this, x2 is something like this, and x3 is something like this. Okay, so, and that is also equal to 2 minus 1 over 2, which is the 3 by 2. Okay. Let's see, we have 15 minutes left. So I can either talk about quivers and Braskamp-Lieb inequalities a bit, just showing the connection, or I can show some funny, strange phenomenon, but maybe I'll talk about quivers and Braskamp-Lieb inequalities. Okay, so this part I'm going to kind of be very brief about it. I'm not going to make any precise statements. I'm just going to show you how things connect. Okay, it's nothing precise, but I will show you where things show up, and as usual, you put in a little bit of work and then you can make it precise. Okay, so we had this bunch of matrices. And we had an action of SLN cross SLN on it. Right? I want to set this up in the language of quivers. So what is a quiver? Okay, it's something that I claim all of you know by different terminology. It's a directed graph. Okay, so quiver is a directed graph. A bunch of arrows. Yeah. People know the English meaning of the word quiver, right? It's a bunch of arrows. Okay, so here's an example of a quiver. You can have multiple arrows. You could have them going in the other direction. Self loops, whatever you wish. Okay, that's too big an example for me to do the next thing, so I give myself a slightly smaller example. Okay, so what's a representation of this quiver? A representation is you put a vector space at each of the vertices, and you give a linear map between the vector spaces for each of the arrows. Okay, so VI's are vector spaces, LI's are linear maps. That's a representation. It's a very, very simple notion. Okay, how do I look at this as some kind of representation? I have to look at the Kronecker quiver. And the Kronecker quiver is one that has two vertices and m arrows between it. Okay, so there are m arrows. This is called the M Kronecker quiver. What's a representation of this? You put two vector spaces here. So if I fix the two vector spaces here to be Fn and Fn, then giving a bunch of linear maps between them is the same as giving a bunch of n by n matrices. Okay? So that's the connection between a tuple here and a representation of such a quiver. And the action of SLN, one SLN acts here and another SLN acts here. Does that make sense? Yeah, so that's.
These are the basis changes that you talked about before.
Yes, these are the
N
basis.
is the basis of the xi left and right.
Okay, but what is the, and what are these, okay, so maybe let's do this. So somehow deciding whether something is in the null cone for this action, which is this action on this representation of this quiver of a certain dimension, blah, 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 there are a lot of numbers and things you have to associate to it, becomes non-commutative rank, right? Now you can take any other quiver you want. So Q, any quiver with no oriented cycles. Is that called a DAG?
Yeah.
Yeah. So it's a directed acyclic graph. And so you might have something that's kind of strange like this, blah, blah, blah. And if you have something like this, there's a standard reduction down to the Kronecker quiver, and the number of arrows here will be some function of the number of arrows here. The dimensions here will be some function of the dimensions here, and each one of these arrows will correspond to like different paths you could have taken from one source to the target. Okay, there's a standard reduction, and so the null cone problem for this with a bunch of other adjectives will become the same as the null cone problem for this with a bunch of other adjectives. Okay, this is a way to reduce it, and this was known long before any of this story happened. Okay, this is due to King or whatever, I don't know. Schofield maybe, I don't know. Okay, so once you have this, now here's another set of things that a particular type of quivers that you can look at is what's called the star quiver. So maybe I put the vector spaces Fn here, Fn1, Fn2, f to the n k, let's say. A representation here looks like a bunch of matrices, A1, A2, AK, and each AI matrix is a matrix of size n cross ni. Did I get this right, or do I go the other way around? Is it ni cross n or n cross ni?
Ni cross n.
It's
multiplying on the right.
So it's ni cross n? Okay, so then I want n cross ni, so I will switch the arrows. Yeah, whatever I need. But what is interesting about such a thing is you look at this tuple of matrices, and sometimes if you know about such inequalities, you see these funny inequalities that occur in this form using integrals. Product of fj of ajx to the pj, okay, now let me write it down and then I'll explain what these things are, is less equal some constant times product of integral of xj in rnj fj of xj dxj.
You should say
In the
that we move
picture.
to the real field now.
Yes, yeah, we move to the real field. Okay, so I think this is correct. I needed this. I needed the arrows this way. Okay, so associated to a tuple of such matrices, okay, and a bunch of rational numbers. You just try to write down such an inequality. Sometimes it works, sometimes it doesn't. Okay, part of this inequality is there's a constant here, so it works if the constant is finite. It doesn't work if the constant is infinite. Okay, there are many inequalities that come in this form, such as Holder's, Loomis-Whitney, Sharp-Young. I don't know any of these inequalities, but I don't know which one is Holder's. I'm sure I know it, but some name. Yeah. So
You should add for door that's also the hypercontractive.
the hypercontractive.
Is also.
Yeah.
one,
Okay.
yeah. That's one.
Hypercontractivity. A particular one, or just all of them? Or I don't know.
Yeah. I mean,
Something.
Most of them.
Most of them. Okay. So a bunch of these famous ones, and a lot more of them. They all fit into this pattern.
Also Minkowski inequality is also there. So.
Yeah, you can rattle out another dozen maybe. Okay, so they all fit into this funny form, and these go under a general form called Braskamp-Lieb inequalities. Okay, and this is roughly what this vector does is this vector helps you in this kind of reduction, or I mean it's you need this additional data to do this kind of reduction. So once you do this kind of reduction from this guy all the way down to this guy, such an inequality will have a non-trivial constant there. By non-trivial I mean not infinity, if and only if that when you come down to the reduction, this one is not in the null cone.
I'm confused now.
Yeah.
So you went back to this picture, which is not this photo.
That's right. So I started with this quiver and a representation here, right? So given such a quiver, a representation, and some additional data, which in this case happens to be this, you can kind of do this reduction that I was talking about for any DAG.
So you would reduce that to the
So I would reduce. So I would take this guy, put it here.
You're just doing this for that. Okay.
Yeah, I'm doing the standard reduction for that, and I get some data here. And whether this data is in the null cone or not will tell me whether such an inequality will be non-trivial or not. And some other data you can pass through. You can try and figure out what the best constant there is and so on. And this would be work of, I don't know who all are part of this. Is it the same?
GOW,
It's the same.
Different paper.
It's a different paper, but it's
Okay.
also GG or W.
Gall, Gurwitz, Oliveira.
And Wigderson, yes. Yeah,
Are there
so.
conditions on the F?
Are there conditions on the F? I think it's just measurability, no?
But it's integrability. Or the
What's
F.
the difference? Yeah.
So yeah. No, they are integrable and non-negative.
Oh,
Integrable and non-negative. That's the only condition. It has to work when you write this. The statement is that the inequality satisfies for every choice of non-negative integrable F.
I mean, it's kind of funny, the things on the left could be, you know, I mean, they're sharing the common X,
Yes.
right? And the things on the right are kind of integrated independently.
Yeah,
That's right.
That's the whole point of all these examples.
Yeah.
So one of the things that you need is,
That's the most basic one, yeah.
but one of the things you need is you need all of these to be kind of surjective.
Yeah, yeah.
If they're not surjective, then you will get a trivial inequality.
Yeah. There's a non-triviality thing, but I mean, it's no loss of generality, so it's.
and are the Braskamp-Lieb inequalities associated with more general quivers?
I don't know how to write one down. Yeah, I have tried to write one down for, I mean, more general quivers. I might as well start with this one, right? This Kronecker quiver. I tried to write it down and it doesn't work for that example, because you have these three things that are kind of outside the null cone, but the image of each one of them is a two-dimensional plane. So on one side you have functions whose values you're taking on these three two-dimensional planes. On the other side you're integrating something over the entire thing. You shouldn't have an inequality because you can concentrate everything along these planes, or you can concentrate everything away from these planes. So it doesn't seem to work for other quivers in any naive way that I can think of. Yeah, there seems to be this kind of additional condition that you need here, which is that the AIs are surjective or something, so that you don't have this kind of phenomenon, and that is somehow subsumed in this null cone condition. So the null cone condition requires that and something else. So it seems to just fit in easily. Yeah.
Are there any results that sort of say something that if you're, let's see, what's the null cone condition? These kinds of inequalities work when you're in the null cone or when you're not in?
When you're not in the null cone.
No, right.
But I can write down the condition.
So there's a distance from which you are in the null, there's a distance away from the null.
Yes.
Does that say anything about how far off? Are there?
I think. It has something to do with this constant, right? So I haven't told you what this constant is, and we don't always know what the constant. And some of these you know for other reasons what the constant is, and this constant is finite if you're away from the null cone. But what exactly the value of this constant is something that kind of depends on things like that, on how far you're. Yeah, and I'm not the greatest expert on this, but you can try to determine this constant and you can get it very close in polynomial time or something, but